So maybe first this, I have to confess, I never had the opportunity to study English at school. So I could learn it maybe from the television, but I have no television. So I learned it for myself the last 2-3 months. I tried to do it as good as possible for you. If you have some problems, just give a sign. Thank you. So I am a teacher in mathematics in a normal school, in what we call a general secondary school in Belgium, and that's for 40% of my time. And for 60% of my time, I'm a teacher of an assistant at the University of Ghent, where I help some students of economy with their exercise of mathematics. So in this talk, I will give some examples of how to use algorithms in mathematics and in art, neither as a mathematician nor as an artist, but as an educator. I'm more an educator than a mathematician. I'm very nice to see and give me a good feeling to see on the internet invitation that we encourage participation of mathematicians, scientists, artists, and educators. Thank you for this. So I started to conceive and to produce some educational and didactical models with and for my students of the school in 1996. This project was called It's Mathemagic. Some of these models are exposed now in a permanent exposition at the University of Ghent. But the last 4 years I have been creating models and shape with deprived and underprivileged children between 6 and 12 years old. In primary school also at Ghent. That's not my job, it's not my hobby, because the job is too hard. I think it's a necessity. Just remember the words of Obama this morning. So to form a picture of the context of this primary school, 100% of this school don't speak Dutch, the official language at home. In this school we have 17 different languages. 65% of the children are underprivileged. That means not only poor, that means they have no social security. They can join social or cultural clubs. They have sometimes no work. They have sometimes also no houses. And 45% of the children are refugees. That means that they are staying in the country illegally. And then, of course, the question to ask is this: how can we help these children? I think maybe 3 answers can be given. First, one of the possibilities to help these children is the use of mathematics, because mathematics, just like art, is universal language. We nearly think in the same way, using the same patterns, and thus also using the same algorithms. Algorithms are not used for the mathematics, but also in their lives. They give structure to their lives. It's not the first time children say, you help me with your mathematics. You structured my life. That's important. And maybe in third reason, the use of algorithms is a way to solve problems. Understanding and solving problems gives those children a greater self-esteem, self-respect they never had before. Now, how can you help this in a concrete way? When possible, the first thing the children have to do is to learn the tables of multiplication. So how can you visualize this? You can not only speak with them, you have to visualize the tables of multiplication. When possibility is to do this: you take a wheel of a bicycle, you grind up the spokes of the wheel, so you have 36 perforations. You numbered all the perforations, 1 to 36, and then it's easy to connect the first with the second with the 4, 3 with 6, 4 with 8, and so on. And you have to take off multiplication of 2. Of course you have difficulty. 19 by 2, 38. you have not 38 perforations. Thus you have to calculate it, modulo 36. To remind this too. 20 gives 40, modulo 36 gives 4. For children of 6 years old, it's amazing to see that we can make a curve, a curved curve, how can I say it? A curve, a real curve, with straight lines. That's amazing to see for the children. We can do it with the tables of 2, cardioid, 3, how do we say this? Nephroid? Nephroid? No? Nephroid. Thank you. Nephroid. Tables of 2, 3, 4, the tables of 5. You have cusped curves. The second possibility to show mathematics is the possibility to use a geometric algorithm. We all know what happens if you throw a stone into a pond. You have a circle, expanding circles, that's very nice, stop, play back. When you throw a circle into a pond, then you have of course just the same expanding circles, but also the shrinking circles. The question now is, if you use not a circle to draw into a pond, but an ellipse, what do you have? I just interrupt the presentation to show this. So the blue is the basic ellipse. And then you can make the different wavefronts. So, second thing, if you take the point A on the ellipse, it's clear that the normal in each point of the ellipse, the normal with respect to the ellipse, gives us the envelope of the normal. It's the curve of Lamy, French mathematician. I know it's nice to see that all these wavefronts have cuts on the curve of Lamy. That we show that's only in case of emergency solution, the curve of Lamy, and of course the cusped, theta cusped curves. Now, when you show this to children, a certain thing to do is to visualize this in space. So we have seen the wavefront surface, cardioid and nephroid, and other possibilities. Let's have a look how to do this. This is the wavefront surface. We take the different equidistant parallel curves and we put them up each other. And this way that the vertical distance, yeah, so the thickness of each plane is the same of the horizontal distance. So that means that if this is the basic ellipse, you have here a straight line. Inclination is of course the same and is the same at all points of the ellipse. That means that you have nice properties. This is done by some students of 16 years old. So they calculate the model, they calculate the surface. And if you look from the top to the bottom of the surface, you will see this, the curve of Lamy. And I have nice properties. As the inclination, the slope is the same in each point, you can make the surface with sand. As for little children, 6, 7 years old, you make an ellipse, and then you disperse sand onto the ellipse, and you see this. It's only the first stage. Of course, the sand will not make the overhanging parts. 3 characteristics. First, the elliptic ridge is a nice ellipse. The ridge is an ellipse, now, a part of an ellipse. Second, if you take the intersection of the line segment here with the ellipse, and you look at the horizontal projection of it, you have the points, 2 points, point of curvature of the basic ellipse. And third, if you take the whole elliptic bridge, you take an intersection with it, and then you calculate what the focal point of the basic ellipse can be, of course, then you have the same point. These things can be calculated and used this sometimes in my class by children, boys and girls of 16 years old. So maybe the answer of your question this morning, and what with mathematics, it's not only the picture, we try to find also the characteristics and to do mathematics. So, yes, cardioid and therefore a three-dimensional representation for children of 6-8 years old. You have two plates in plexiglass. You drilled some holes in it, perforations, and then you connect them in the correct way, just in the same way we did in a bicycle wheel, but now in a three-dimensional possibility. It's not a cone. If you look at the sides, you see clearly that you have a kind of curved surface, a curved rule surface. And if you look from the top to the bottom, you see, of course, the same as in the wheel. You have a nice cardioid. For the nephroid, we do the same in a sewer pipe with the children. The drills. It's not a nice picture. I have some difficulties to photograph this picture, but you do just the same. And you have the tables of 3. Instead of using the rim of the wheel, you have kind of projection, and you have just a nice nephroid in a sewer pipe. Hyperbolic paraboloids, a very nice algorithm. You use an easy pattern of squares. Here beneath you have some weights, and then it's easy and nice too for the children to see when you close the upper plate that you have here not only a curve but a curved surface, the hyperbolic paraboloid. Just the same with the two parabolas with a hyperbola. And the nice thing is that these models are made by children from 60, 70 years old, and I use them to explain it to the children in this special primary school. This is done by a little girl, boy, I forgot it, I think 8 or 9 years old. Just sticks, barbecue sticks, they make a cube, and then you can easily make a hyperbolic paraboloid using the two diagonals. In a pipe and a cylinder, you have here a sinus. Thus if you roll the cylinder on a surface, you have a nice sinus curve, and then if you connect them in a correct way, so in a horizontal way, you have a hyperbolic paraboloid. If you look from top to the bottom, you have here the axis of the moon surface. And sometimes, oh, sorry.
I think it's a difficulty. It's a flatter quality.
That's possible? I make a mistake? I'm sorry. Thank you. So it's not my first mistake. You will see another mistake here. I have a little problem. 2 problems now. Thank you. 1959, a big statement. I got on 59. In 60, with a lot of respect for my mother, I am from 60, and 60 when my mother sang just the same, but in Flemish. Yes, it exists in Flemish, but there is the Liza who has to take the water. In Flemish is the man, and my mother. In 1700, for the colleagues from Germany, in 1700, there is a book, Berglieder, Buchlein, a little book with songs from the mountains. And to translate the text of the Wavefronts, you have just the same text as in that book from 1700 for the colleagues from Germany. It's a German book. So, Another way to show or to use algorithms is to use two equivalent curves. This here, the curve of Schur in German, and I learned something. See, I picked sometimes some words. The NGC, a negative Gaussian curve, a curvature. I'm sorry, curvature. It's also the answer from the problem of Eva. I think if you use a cube, you take the half of the cube and you put it in a soap, water soap water, what would I say? Then you have a corpuscle of order 16. I will show it. So there's here the two different curves, and then you have the possibility to make this. Because you have the two curves in perpendicular planes, and the surface of shown is a translation surface. It's the only non-trivial translation surface. They have to prove it. But of course, if the children can prove this, they have to make it. And you can easily make it with silk film as it is a minimal surface. So just make this shape, the same shape of you. So you put it in a soap, and you have a nice minimal surface. And maybe I'll last here for this model of error. I saw it in your picture, in your slide. I began with a wavefront surface. But the difficulty there, you have different niveau lines, but there are no ellipses. And now we try to do just the same, that each niveau line is an ellipse. How can you do that? You take two ellipses perpendicular to each other in different parallel planes, and then connect P1 with P2. The only thing to observe is that the length of the minor axis is a third of the length of the major axis. Right? And the angles here, they are the same. Just the eccentric angles must be the same. If you do this and you connect P1 with P2, then you have this model. It is the model we saw in the slides of Georg. So you have here indeed a line segment. In the middle you have a circle, and here you have also a line segment. If you look from the top to the bottom, I suppose you see here, it's not correct, it's not a square, but you see here, think, a nice kind of marine curve, maybe asteroid, I'm not sure, maybe in this thank you. So some properties of this surface. If you take the niveau lines, or the contour lines, on a quarter, 2 quarters, 3 quarters of the distance between the two ellipses, you have always the same distance. The distance equal to the minor axis of the ellipse. The angle between the rulings of the plane of the ellipses is a constant, and so the length between the 2 points are also constant. So pupils have to prove this and to make some exercises. 2 experiments in this primary school is, of course, have they understood it, and we make, or we try to find the mystery of Euler. That means that the vertices, the number of the vertices, minus the number of the edges, plus the surfaces, the number of the surfaces equals 2. So I give this photograph, and I ask to try to find the mystery of Euler. It was not possible to do it because children have a lot of difficulties with the edges behind the photograph, not the photograph, but the photograph. So second exercise, I give this, and then they began to count the numbers and the numbers of the vertices. But it's only after making a lot of these models, it's a very big model, I think 80 centimeters diameter. So after making this, some children, not all of the children, that is clear, some of the children understood the general calculating method, not the counting method, but the calculating method to find the mystery of order. The second experiment is the mobile hyperboloid. You have two plates, pixel plates, and here beneath you have a plate that you can turn to the left and to the right. Then is the question, if you do this, what happens with the straight, the tightness linked between the two plates? Let's try, just in case of emergency. This is the model, and then if you turn to the left or to the right, you can try it after my talk. I have two slides, so if you want to see this, close your eyes. The two slides are only in case of emergency, but the airplane didn't fall, so I have the model with me. So close your eyes. These are the solutions. Maybe after these two experiments, a little conclusion. It's a conclusion also by Professor Eisenberg of the University of Colorado in his paper. Mathematical graphs have to be seen as a strong element of mathematical education. And for me it's clear that the use of algorithms gives the young, underprivileged, young children, that between brackets for all children, a better structure, not only in the use of mathematics, but also in their lives. For me, it's very important to say this, to kind of conclude this. So, other type of use of algorithms with 16 years old children, and my first project is mathematic. Finite geometry. The question here is how can you plot 7 points onto to make 7 lines, so that on each line you have 3 points, and each point is an intersection of 3 lines. That is not possible. So you have to make a model, but you cannot solve the problem. So we have to make an abstract model, and that's not so easy for these students. How can you make an abstract model? Each model is a concrete model. So an abstract model was this. So we try to find the solution. Here there's the 7 lines with the numbers of the points. That's not possible to make, and we have the idea to do it on this way. These points are lines, and these points are the real points. So it's an abstract model where the lines are represented by points. So the 7-7-3 configuration is not possible, thus we try to make another configuration, the configuration of the side. 10 points, 10 lines, and the same problem. On each line you have 3 points, and 3 points are the intersection of 3 lines. And to make a real model, you can number the points as follows: 12, 30, and so on, and then the solution is given by this. The lines are formed by 3 points with only 3 digits. Thus, if you take 12 and 30, you have a double line, and then you have to find a double 2 and double 3, that means 23. You take 12 and 14, and then you have to take the last point, you have to double the double line, and so you need a double 2, you need a double 4, you take 24 as third point. And as an algorithm that gives us the good solution. And so we make it as a solution in the root with metal rods. As this was so good, we try to make the third configuration with 15 points and 15 lines. Also the same problem. For this purpose, the points are numbered in this way. So we have 1, 2, 10 points as before, and here 55 points. So you have in total 15 points. That's the problem. Solution is given by this. You take 3 points from a line if their numbers contain all digits from 1 to 6. So you take 1, 3, 4, 5, 6, and then you can take 1, 2, 3, 4 is not possible, so take 3, 5. You have 1, 2, 3, and 5, so you have to take 4, 6 to have the 6 digits, different digits. So we have a nice algorithm to find the solution. Now we have to make the model, and this is the first time I give a talk. But I saw this morning you ask some quiz questions. And maybe a quiz question is this: how can you put 5 boys and the teacher into a little toilet? The answer is that model. A little explanation. The boy who did it, he used a spray of phosphorus spray, so he can see the model in dark. I went to a classroom, but it was not dark enough, so the solution was to go to the toilet with 5 boys and me, the teacher. No, that was not the difficulty. The difficulty was the second quiz question. What happened if we go out to the toilet? That's a problem. What happened? It's a problem. Just when the first boy went out, the director came on. That's not the problem. But the second boy came out, director. It's not possible. And the third and fourth and fifth boy, and then me. So you have 55 points, 27 lines. You have on each line 5 points, and each point is the intersection of 3 lines. It's also called in mathematics the general quadrangle of order 4 and 2. So you have 5 points and on each line, and 3 points is the intersection of each line. So, first exercise for my students: how many colors are at least needed to color a map on a torus, so that each adjacent country has another color? The solution is this. This is an unfolded torus. If you close this, you have the same color 7, 7, 6, 6, 5, 5. So you have a cylinder, and if you close the cylinder, you have the same colors 5, 5, 2, 2, 7, 7. So you have a nice closed torus. What is the answer? The answer is given very easily. You take region 1, and you have above region 1, 3 and 4. You take 2 above 2, you have 4, 5. 3, 5, 6, 4, you have above 6, 7. 5 is here, 7, 1, 6, 1, 2, 7. Just above you have 2 and 3, and indeed this is the same configuration, the final configuration for the first slides of the second chapter. Exercise 1. Here you have the result made by a girl, no secant. Exercise 2. Two new Olympic disciplines, the shot put and the discus throw. Professor Van der Laan with not 1 ball but 40 balls, shot put, and a discus throw with a nice discus. I have a lot of respect for these men. It was on a colloquium, an international colloquium in Belgium, and he used these models as didactical models. Other models done by the students, they have to calculate these things, so they can go to the factory to make the cube and make the parabola. It's a 4-degree surface. That was inspired by Gabel, one of the first Russian constructivists. That is model. I think Derek will give some explanation, so we can go further. In the third chapter, very quickly, and we have not so much time, very quickly, maybe some investigation I did. Van der Laan, you can see it on the internet, it's very easy to see, has formulated some ideas in his book Le Nombre Plastique, Architectonique, and also in other book, the Dutch version, 15 lessons about the disposition of human habitats. Very quickly, I did it in 15 lessons. I tried to do it in 7 steps. First experiment he did, he took a sheet of paper, 50 centimeters, and he asked 50 people to turn it into pieces. And then you have two pieces of apparent equal sizes, but of course you have a difference of 4%. But they looked, or they have apparent equal size, but that is not so. Step 2, second experiment, he took 36 squares with a difference of 4%. And then his philosophy was this: these 7 squares have apparent equal sizes, so you can take them apart, and can do this for the other 7 equal of similar squares, so you can do it for these ones, so you become 5 difficult types of squares with apparent equal sizes. This one is the unit square, and then he came to this. Step 4, as you have seen, you have a margin, so that he took 7 different squares. Of course, it's possible to have 8 or 10 different squares, but he took in this example 7 different squares. Each type had apparent equal sizes, so he called this a type of sizes. And what's very important for Van der Laan, a Dutch architect, is that the unit, the difference between the two greatest types, two greatest measures from two greatest types, the difference of this must be the linear unit. If this is the case, then you have a perfect order of size. And he used the difference measures here as a perfect method to have buildings. Of course, this is a discrete model. You have different sizes in a normal habitat and a normal residence. All the sizes are continuous. In this way, if the sizes are continuous, these two measures are the same. He called these two measures greatest measure and the smallest measure of different types the threshold measures, and the drempelwaarde, so a threshold measure of his sizes. So he has to find a geometric sequence, and the way to do this is this. If you have one dimension, then you have also only 1 meter of 1 unit. There's a different measure is of course 2 meters of 2 times the unit measure. So 1 plus 1 is 2, type 1 plus type 1 is 2. If you do this with 2 dimensions, you have 1 plus 2 is 3, and that gives us the golden number, as the sequence 1 plus the second gives us the third. But in dimension 3, and that was just the idea of Van der Laan, 1 plus 2, so the threshold measure of the first type plus this type 2 gives us the fourth type of measures, of threshold measures. So there's the plastic number, that gives us the plastic number. And so it's possible to find a fixed common ratio. So 1 plus 2 is 4, 2 plus 1 is 4. These are the pictures from Van der Laan itself. As 1 plus 2 is 4, then it's easy to prove that 6 min 5 is 1. And that's important because then you have a perfect order of sizes. Because the difference of the two highest, the two greatest threshold measures is just the smallest one. So you have a perfect order of size you can use in buildings. And that's what he used in all his buildings. All his abbeys, his nunnery, and so on. But step 7, that was not enough. And the reason is very strange. He needs a double unit. And for this, he has two reasons. First is if you measure the thickness of a wall, then you measure from the front to the back. But if you measure the width of a wall, you do it in 2 times, from the middle to the left and from the middle to the right. So you need a double measure. That was one of the reasons he needs a double measure. And one of the very nice characteristics is this. This type, the 5th type, equals the harmonic mean of 7 and 8. And if you calculate the harmonic mean between these two, then you have just one difference. This difference is just the linear difference. So for him, a total system is a system of 8 measures. And effective, he used this in all his buildings. I went to Westminster in Belgium, and I fitted there. I measured some tiles, the door, the thickness of the door, and so on. This is mathematics. This is what Van der Laan did. And you see that indeed 1 plus 2 is 4. The difference of 4 and 6 mathematically seen is indeed 1. And if you take a harmonic mean between 7 and 8, the difference is here 1 with the last type of measure. Morphic numbers, I think it's on the internet, so you can easily find this. What's important that we have only 2 morphic numbers. First, the golden mean and the plastic number, the number of Van der Laan. Step 9, especially for Balmer, of course, it was a must. Yeah. That's a nice picture. That's also a nice picture. That's the equation of the golden mean. The golden mean. That's also the equation. 1 plus 2 is 4. 1 plus 2 is 4. And at last, of course, 1 plus 3 is 6 min 1 is 5. That's better. Some pictures, but I think you find this on the internet. Here the tires are 50 centimeters. The thickness here of the door is 7. The height is 2 meters, 2.11, and this is 0.91. And if you make the division, you have indeed the 3rd type of measures. So effective, it's easy to control this. He used only these measures. I think that are some pictures, but that's the end of my slides. I thank Bama for his invitation. I think it will give my projects a new dynamism, so that I could help children, the underprivileged children, better than before.